In the last video, we saw that when you make decisions in hypothesis testing, you could be correct, but you could also be making either a type 1 or a type 2 error. Now, a type 2 error is when you did not reject the null hypothesis. And since you did not reject the null hypothesis, that's called a false negative. And then if you did reject the null hypothesis and you shouldn't have, that's considered also known as a false positive. Right? Remember, we're always interested in what's happening with the alternative. So when you're rejecting the null hypothesis, you're saying, I'm positive about that alternative, and that's not the case. And then by the same token, if you say, no, 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 I'm not going to go with that alternative, I do not reject my null hypothesis, then that's a negative language thing, the word not. So it's a false negative. All right, let's think about these just a little bit more. All right, so alpha, the same alpha that we have known and loved since chapter 9, is called the level of significance. It is the probability of making a type 1 error. Or in other words, it's the probability of rejecting the null hypothesis when it was true. And just to be very clear, it is called the level of significance. We will be given alpha in almost every problem we work with. Real life, if you were going to work in statistics, you would choose alpha levels based on severity of making that type 1 error or whatever. But for our purposes in our course, it will be given to us in the problems. So it'll either be saying level of significance or they'll say alpha. They can use the symbol or just the words. Beta is this symbol. It looks like a B with like a tail on it. That is the Greek letter B, beta. And that is the probability of making a type 2 error. In other words, not rejecting the null hypothesis when it was false. Beta is more difficult to calculate and work with than alpha, so we are not going to be dealing with it very much, other than to say that it deals with the power of the test and the bit that we are going to talk about in this page right here. All right, so to start off with, why don't we set alpha and beta to 0? So a lot of students, when I teach this in face-to-face class, they really get upset about innocent people wrongfully convicted. I mean, this is a horrible thing. And by the same token, guilty people walking free, I mean, it's all good in soap operas, but it's not good in real life. So these are terrible things to have happen. How could we make them 0? And the answer is you really can't make them 0. You can lower them sometimes, but you can't make them eliminated. And part of the deal is that the two of them are kind of on a seesaw or a teeter-totter together, like back in school. Grade school, you have those boards or a lever, if you'd like to think of it, or a weight, a balance. So if alpha goes up, or excuse me, alpha goes down, you want to lower that alpha. You want to say, look, let's think about this in terms of the criminal case. I want to never, 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 never have an innocent person be wrongfully convicted. I'm so nervous about this. I want to make this go low, low, low. But what's going to happen? If you never want somebody wrongfully convicted, you're going to let a lot of people go free, which means you'll automatically be letting a lot of guilty people go free, right? By the same token, a lot of people say, oh, we want the criminals behind bars, you want to lower this. You don't ever want guilty people walking free. But if you're never going to have guilty people walking free, it automatically means you're going to end up convicting innocent people because you're so interested in getting convictions that you don't care enough about whether they're truly innocent or not. And that's why I say alpha and beta are on a bit of a pendulum with each other. They're on a, well, I think of it as a seesaw or teeter-totter. They're on a balance. And if one goes up, the other one goes down. All right, I typed all that up for you so you can see it. So alpha and beta are on a balance, teeter-totter together. So that means that if alpha goes to 0, as alpha lowers down, beta will go up. And vice versa. If beta goes down, alpha will go up. Now, they're not going to go to 100% necessarily because you still will make correct decisions, right? You're still going to have the other two options of making correct decision here and correct decision here. But nevertheless, if you try to lower this one, you're going to raise this one and vice versa. All right. Another way to see it, in case that's a little bit unclear, is that if you did somehow have alpha 0 or beta 0 for that matter, it doesn't really matter which one, that would imply that you are 100% sure about your decision. And that's statistically not possible. We are never 100% sure of anything. I'm not even 100% sure that the sun will come up tomorrow. It is possible that a meteorite will hit the earth and we will all be destroyed tonight. I know it's kind of depressing to think about, but it's possible. I'm not 100% sure, right? I'm just 99.9999999% sure. in the case of hypothesis testing, all you have is evidence to support or not support. That's it, right? To reject, I guess I could say reject or not reject. That's all you've got. You don't have 100% surety of anything. You're not proving something. That's why we never say the word accept back here in the conclusion piece. We never accept anything because we're not really proving anything. We are just proving that it's likely or proving that it's unlikely. We're saying we have evidence or we do not have good evidence. That's all. Right, back here. Let's look at Charlie. So Charlie will perform a hypothesis and a hypothesis test at the alpha equals 0.05 level of significance. Felice will perform the same test at the 0.01 level of significance. All right, if H naught is true, who has the greater probability of making a type 1 error? Okay, well, remember that the probability of making a type 1 error, oh goodness, type 1 error is alpha. That's what alpha is. Okay, so all we have to know is who has the larger alpha, and that would be Charlie. See, Charlie has an alpha of 0.05. So since Charlie has the larger alpha, which is 0.05, he has a higher chance of making a type 1 error. All right, good. All right, now, who has the higher probability of making a type 2 error? Well, Felice has the lower alpha, which means probably, and this is not 100% the case all the time, but for our purposes, it's going to be that since they're on this teeter-totter together, if she has a higher or lower alpha, she probably has a higher beta. Now, with testing for drug trials and stuff, it's not always working like this, but for us, we'll think of it this way. So Felice has a lower alpha, which was only 0.01. Therefore, she has a bigger chance of making a type 2 error. Right? Oh, therefore, so her beta is higher. Is most likely higher because well, actually we know it's higher because it's the same test. So her beta is higher than Charlie's. Therefore, she has a bigger chance of making a type 2 error. And again, we can get a little more refined in that in terms of like chemistry for tests and things like that. When they do real drug testing, they always want to lower both alpha and beta. I mean, you can imagine with, let's say, a disease test or a pregnancy test, you don't want people to have false positives or false negatives, right? False positive is you are, it tells you you're pregnant and you're actually not, or, you know, something like that. So you got to be careful of both of those kinds of things with drug testing, or as in testing a drug, or even testing whether you are positive for drugs, that as well, because those are both capable of having false positives and false negatives. All right, so the last bit, thanks to XKCD, who the author of which generously allowed us to use this. So here you see the jelly beans cause acne, scientists investigate, you know. So we found no link between jelly beans and acne. The p-value is greater than 0.05. Now we'll talk about what p-value is a little bit later. We've already seen it. It's the reason we knew that Steve's dye was rigged way back at the beginning of this section. But so that settles that. I hear it only a certain color causes scientists, right? So they try out all these different kind of jelly beans. So they've got the purple jelly beans, no good. The brown jelly beans, no good. The pink jelly beans, no good. Blue jelly beans, nothing. Right? And they keep going. So they have teal, salmon, red, turquoise, magenta, yellow, gray, tan, cyan, green. Uh-oh. But the green one had one. See right there? So let me highlight it for you. All right, I highlighted it, but I know I moved it over, so orient yourself for a second because I wanted to write up everything that I want to say about this. So if you look here, we have 20 studies total. We have 5 rows by, so 5 columns by 4 rows. So that's 20 studies total. We have 19 of them showing no relation between jelly beans and acne. None, 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 right? Then we have one that does, and then none, 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 right? So if you set, as we read these studies, just as a comment, as we read these studies in the media, so online, on websites, etc., be careful, because if somebody's just talking about this one study, they could be talking about the one and not about the 19, right? Especially if they have an axe to grind somewhere. There we go. I wrote that in. By the axe to grind, I mean, are they politically motivated? Do they want certain things like, I want there to be no such thing as global climate change, therefore I will ignore all the studies that show there is global climate change, and I'll pay attention to the one that isn't, that kind of thing. Or, their religious views, their political views, etc. If alpha was set at 0.05, we'd expect 5% of these studies to be false positives. Type 1 error is a false positive. So how much is that? 5% of 20 is 0.05 times 20, which is 1. So it's most likely the case that the green jelly bean study is the one false positive that we're seeing. It's a type 1 error, and we should ignore it, not talk about it ad nauseum on the news, right? Oops, I don't know why I did that. There we go. And I can't say this enough, you really have to watch this as you consume media, as people tell you stories, oh, they did a study, blah, blah, blah. So when they say they did a study, sometimes it's the first study they've ever done, there's only one study done, etc. When that happens, that makes sense to pay attention to that one study. But sometimes they've actually done lots of studies, and the person that's talking to you really only wants to talk about the one that's a special case and not about all the rest of them. So you got to be really careful when you're researching stuff. Was it that there was only one study available, or was it that this one study is the only one that's showing what the person wants to hear? All right, so now we've learned a little bit about being careful with type 1 and type 2 errors, and we still don't know how to actually run a hypothesis test, but that's what we're going to learn how to do and what to do in section 10.2. So I'll see you.